Okay, good evening, everybody. Can you hear me? Can you hear me on Zoom? Yes. Okay.
Yes.
So, this is our last meeting, and we are going to have 4 speakers today. This is just a minute. This is Aaron, Sharon, Armugam. Did I pronounce your name correctly? And Sri. Just a few words before we start. I had great pleasure teaching this class. I hope that it was intriguing and interesting and you learned something new. It's very non-traditional. We did not have equations here. We did not do any theory. But I hope that it got you to think how to be better scientists when you grow up. And tell your friends, I'm going to teach it again next semester. And I think that we will try to look for other cases and maybe ask some different requirements, because I don't want people to repeat the same stories again and again. But there are a lot of stories. So, and I think it's important that we are all aware of the problems. Anybody wants to say anything before we start? Also, people on Zoom or here in the room? Well, if not, let's just start because we have to. Sorry?
I think also because of the great.
Okay, thank you. Thank you. So let's start. We are going to start with Aaron, so you can share your screen and go ahead. What did I do? That's not good. Just a minute. Just a minute, something is wrong here. Aaron, can you speak?
Yes.
Go here. Everybody can hear Aaron?
Yes.
Okay, good. If they can hear you, it's fine. You can speak from your own space.
Okay, so everyone, my name is Aaron, and I'm doing my master here in the Faculty of Engineering. And I would like to talk.
Actually, we don't hear so good.
So let's see if. Okay, so I think we are using my microphone here. Sure.
Okay, so I would like to talk today about the father of the computers, about the father of computer. So there are a lot of different people that we can say that was the influence of the computer architecture over the years. We can start with Charles Babbage, that's 200 years ago, and Alan Turing with the Enigma. But I would like to talk today about John von Neumann. So John von Neumann, he was a Hungarian American scientist. He studied in Hungary and he immigrated to America before World War II. He's considered as one of the brightest scientists in the 20th century, and he was affected a lot of different subjects. For example, in the computer architecture field, in the computer science, he invented, for example, the merge sort. And he was also took a part of the development of the nuclear weapon, also known as the Manhattan Project. So he considered really as one of the greatest scientists in the last decades. And he was also considered as the owner of what we call in the computer architecture the von Neumann architecture. So a von Neumann architecture is mostly is used, I think, in almost in more than 90% of the computer that we have. It's considered as a standard. It's used over the last 70 years, and it didn't look like it's going to change soon. And the main idea behind the one.
That's not accurate. Neural nets are very.
Yeah. So this is but let's say in the CPU world, it's a standard. And again, actually, I post here some different articles with the ideas with some of that mention the von Neumann architecture. So when we want to refer, for example, in neural network, we want to refer to for something that is new, we refer it as a non-von Neumann architecture that I think it's established the idea that this really is a standard. So when we don't want to use it, so we say that this is not this this one. So it's really like a real standard. So the idea in von Neumann architecture is the instruction and the data are blocked in the same idea. So I will dive just a little bit to how it works, how CPUs works. Most of the modern CPUs contain three main elements. So we have the arithmetic or the logic unit and actually doing what we are calling compute. Okay, so it can be sub or subtract or whatever compute operation we want to do. We have also the memory that contains that stores all the data that we want to work on with the ALU. And you have a control unit. The control unit is able to, for example,
the cache.
Yeah, exactly. Yeah. Okay, I'm speaking about CPU and don't want to get too much into details. It's just the basic idea of how it works. Okay, and we have also the control unit. So the control unit is, for example, can take the values as stored in the memory unit in address X, and then take the values are stored in the memory unit in address Y, and then fetch them to the ALU, and then perform some operation, and then store the results in address Z. Okay, so this is the idea of how it works, and the idea of but what's important to say that instructions, like add or data, like for example a number, are represented both in the same way. Okay? It's just how we translate them. For example, the 4 bits, if we take 4 bits 1 1 1 1, we can count them like 15, the number 15. But for example, I can use it, for example, to say that this is instruction that perform an add operation. So it's important to understand that basically instruction and data both can be fetched from the same memory, and this is the basic idea of von Neumann architecture, and it was a really big breakthrough that instruction and data are fetched from the same memory. So I would like to start how it started, the idea. So let's talk about the ENIAC. ENIAC, it stands for Electronic Numerical Integrator and Computer. Was the first programmable electronic general purpose digital computer. So there were computers before, right? I'm speaking about the 1945. So there was already the bombs of Turing. The idea was already there. But the ENIAC was the first electronic computer. And it built in 1945. ENIAC was designed and primarily used in order to calculate artillery firing table for the US Army. It was funded by the US Army, but the people who designed the ENIAC and worked on it were actually from the University of Pennsylvania in the Moore School of Engineering. So we talk about a real monster. ENIAC size was 170 square meters with 27 tons and consumed 150 kilowatts of electricity, which is a huge amount of power. It was a rumor in Pennsylvania that when ENIAC is switched on, so the light on Pennsylvania were dimmed. I don't know if it's true or not, but it's give some perspective. And
it's like crypto today.
Yeah, but actually there is a nice table that I found on Wikipedia that did some, I think it demonstrates nicely the Moore's law. So Moore's law in general claims that every 2 years we are with the same amount of power, we are doubling our computation power. So consider that 70 years back, over 70 years. So we have here a table that compare the ENIAC versus an Xbox Series X. And it costs, and we can see the money per the US dollar per gigaflop operation. So flop, we refer as flop as floating point operation, which is the basic computation thing that the computer can do. And gigaflop, it's a billion of that. So if we adjust the ENIAC if we look at the ENIAC in this perspective, so performing 1 gigaflop operation in ENIAC would cost almost $2 quadrillion, and in Xbox Series X, which is off-the-shelf product, it costs 4 cents. And of course, we have today also supercomputers that perform exaflops. So it's really nice. I think it demonstrates nicely how much this field evolved.
Can you go back?
Yes. Yeah,
you're referring to say the most fun part of this.
Well,
if I'm not mistaken, it had like 12,000 tubes.
Yeah. Yeah.
So it worked on, there was no transistor at this time. And they were working on basically like light bulbs. Those are with 3-terminal devices.
Yeah.
Vacuum tubes. Twistors or
they claim that to fix,
they would fail all the time. So they have an army of ladies behind this machine switching bulbs all the time to get this working.
It was a really big project, a huge one, and it also took a few days each time they wanted to repair something. It's pretty interesting. And the project was designed by was led by John Mockley and Presper Eckert from the University of Pennsylvania. And the design was frozen in 1944, and Eckert and Mockley were already aware that they have some limitation in the machine in the ENIAC. And they decided to plan the successor of the ENIAC, which called later the EDVAC, that should overcome the problems that they saw in ENIAC. For example, it was the ENIAC worked on an octave base and they moved to a binary base, but the most important thing is that they actually blend the EDVAC with what we call today a von Neumann architecture. And by January 1945, they had contracted to build the new stored program computer. Von Neumann joined in the late stages of ENIAC. He came there from the Manhattan Project, and he was, as a consultant, really, most of the loops were closed in this stage, but he was thrilled of the idea. So in the next project, called the EDVAC, he already had a really big reputation. So in the next project that called the EDVAC, which stands for Electronic Decreased Variable Automatic Computer, they had really great names. It was a successor of the ENIAC. And it was basically designed by the same team from the ENIAC project, but in this time, von Neumann led the design. And during this project, von Neumann summarized the design, the idea of the design, in a draft and mailed it to his colleague, Herman Goldstein, who was also part of this team, the ENIAC team, and he sent it to him as a basic report, as a draft. And in von Neumann manuscript, there was no credits, no reference to other contributors, and he claimed that it was only a draft.
The manuscript was sent to publication or not?
So this is exactly what I would like to focus about. So Goldstein was fascinated by the report, and he typed the manuscript, and he sent it to his colleagues, and enlisted von Neumann as the only author. So what you're seeing here, it's one of the most famous paper in terms of computer architecture, and it describes how EDVAC works, and it also, as a part of that, also the von Neumann architecture. And Goldstein sent them, and the first draft of a report of the EDVAC, which is this draft, laid down the fundamentals of the modern computer. and introduced it to the world, the architecture that we spoke before. And the report was published without Eckert and Mauchly knowledge. So needless to say that Eckert and Mauchly wasn't very happy when they heard that the first draft was published, and they became very bitter on von Neumann for sending the report and on Goldstein for publish it. And by the way, they didn't get any credit or patent or something like that. And in one of his interviews, Eckert claimed that von Neumann was stealing the idea. So he really pointed a finger on von Neumann and said that his idea that is really a standard, everyone uses it. It's really a basic thing. Was supposed to be his and Mauchly's idea. In the past years, also there are some small group that want to change the name, but it's hard to believe that thing that was established so hard, a term that is established so hard, will change. And we can assume that Eckert and Mauchly's name will remain on credit. So I would like to talk about, so actually, so von Neumann or Goldstein did anything wrong per se. It's not a stealing. First of all, von Neumann is definitely one of the brightest scientists, and he definitely contributed the EDVAC projects a lot. So this is not a stealing, a classic stealing at all. And Goldstein, from his side, just got a report, a draft, and he feel comfortable to share it. There is no real problem here, right? It's a very gray area, and but I think that something could have been done differently. I think it's important in every time it's possible to try to credit the people around you. And I think I think it's very relevant for today, especially in the academic field, when, for example, it's like there is a big dissonance. From one side, we always want to be, we want to contribute, right? We want to save the world. But from the other hand, you want to get credit on that. So it's an example for that. I can think of that if someone writing a paper with someone else as a co-writer. So at the beginning of the paper, you write that they both equally contributor, etc., etc. But at the end, someone have to be the et al. And nobody wants to be the et al. But I think it's a food for thought, right? I think I don't have an answer here, but I think in general it's important because you can never know where if it's gonna hurt people or where it's gonna find it. So that's it.
Great, thank you. So that was great. So we actually had a similar case in the lecture I gave. Remember?
Yeah.
Which
in
case?
The DNA.
Yes. Name? You should remember that name. Anybody remembers?
Kirk and Watson.
Watson and Franklin. Right. Same case. She was not credited, and so this is obviously a very big issue. And in general, we should always be very generous.
Yeah.
But there is one topic we did not cover during this course, which is the flip side of giving credit for as many people you think should get credited. There is something else called courtesy authorship, where people get authorship when they don't deserve it. And usually those are big bosses that really don't do any science anymore, and they demand the students to put their name on. There are many, many cases where people practice courtesy authorship. This is a topic we did not cover. Maybe next time I will cover that topic as well. So we need to be very careful. On one hand, you want to be very generous. You don't want to be people holding grudge because they did contribute and somehow the name is out. On the other hand, you don't want to give credit when it's not deserved. So it's, as you said, it's a very delicate balance. And as you get more experience doing science over the years, you kind of handle this balance better, but very good. Thank you for bringing it up. Great, thank you. All right, so our next speaker is, let me.
Me, Sharon.
Right, Sharon, you can go ahead and share.
Is it on the screen?
Yeah, we can see it.
Okay. So hi, I'm Sharon, and I'm going to present the story of Victor Ninov, which was a physicist and a rising star in the field of discovery of super heavy elements, but lost everything due to data fabrication. Let's start with some background about heavy elements. Well, the most massive naturally occurring element on Earth is uranium, with atomic number of 92, which is the number of protons in the nucleus. And elements heavier than uranium are called trans-uranium elements, and ones heavier than Rutherfordium, which is element 104, are referred to as super heavy elements. We can't find any of them in nature naturally because they undergo radioactive decay to lighter elements in a very short time. So how can we make an element? In theory, this just needs an ion beam fired at a target with the right number of protons. For example, the Berkeley team in 1974 bombarded californium, which is element 98, with the oxygen ions, which is 8, and created element 106. But in practice, this technique is far more difficult. Their heats are rare, and they're far more likely to result in the nucleus breaking apart. And even if a new element is produced, it is usually so unstable it radioactively decays in seconds. So in order to overcome the repulsion between two positively charged nuclei, somebody, and I don't remember who, invented the cyclotron or the particle accelerators. They provide energetic, sorry?
His name was Lawrence.
Thank you. It was on the tip of my tongue. They produce the desired nuclear reactions by shooting a beam of variously charged particles onto suitable targets. So the charged particles fly out of the cyclotron, slam into a target of ordinary matter, and the magic happens when a projectile nucleus hits the target just right with so much energy that they fuse together. So after that was established, scientists started the search for more massive elements with 93 or more protons. And the first success was in 1940 when the ptinium with Z93 was synthesized at Berkeley. Okay, so artificially created super heavy elements have decay lifetime between nanoseconds and minutes. But neutron-rich super heavy elements are expected to be situated in something they call island of stability. And a theory says that in this island of stability, extremely long half-life elements exist. So currently the isotope of new elements that have been discovered are on the shore of this island, and we cannot yet reach the center. But the predictions are that if scientists can create atoms with the right combination of protons and neutrons, they might become stable and endure for minutes, days, and even years. For this reason, for decades, scientists have been trying to create heavier and heavier elements by forging atoms with more protons in the nuclei. And many scientists have been working night and day to be the first ones to find the next stable heavy element. So the efforts of finding new elements were an actual race between three main research labs. The first one is the University of California at Berkeley. The second is the Joint Institute of Nuclear Research in Dublin, and the Society of Heavy Ion Research called GSI in Darmstadt, Germany. all three competitors were seeking the prized island of stability. The process of super heavy element creation and identification requires large-scale accelerators facilities, sophisticated magnetic separators, efficient detectors, and time. A small anecdote is that the element hunters at Berkeley worked for decades with cyclotron built in 1961. And they say that the device's control room has such aged light bulbs, meters, and dials that it looked like the set of the original Star Trek. Around the 90s, a very impressive strike of elements was found at Berkeley. But gradually they've slowly lost their touch, and the labs of Germany, GSI and GINR in Dublin were taking more leading role in synthesizing heavy elements. The team at GSI just discovered a strike of elements 104 up to 112. And Berkeley was eager to be, again, in the leading position in finding the next element. So they decided to recruit a rising star in the field called Victor Ninov. He was a co-discoverer of elements 110, 11, and 12 from GSI in 96. Well, so let's see how he paved his way to being this key player in this race. He studied physics at Darmstadt, and for his thesis and postdoctoral fellowship, he worked at GSI. He joined the team there after they had discovered elements 107, 8, and 9, and they were just running confirmation experiments. And in a short time, he distinguished himself for his knowledge for computers and ability to build technical instruments. And because of his computer skills, he was given sole control over the analysis program in GSI experiments. Eventually, it was a co-discoverer of the next elements, 110 and 112. And after that, in 96, Berkeley hired him. By now, he was a world-class expert as a part of an effort to search for that fabled island of stability. He joined the team of Kenneth Gregorich, that they specifically wanted help building an instrument called the gas field separator. He had constructed a similar device in Germany. And when Ninov came to the group, he brought with him a computer program called Goosey that promised to give the Americans a great digital edge, exactly what they needed to lead again in the race. So here in the bottom image, we see Gregorich and Ninov building the BGS. And Gregorich tells that they have spent almost every day during 5 years building and working on this instrument, discovering new elements. So Berkeley team hoped that this move would get them back in the race. And in this time, the Russian team was already pioneering with a new technique they believe could produce up to element 118. They reported that they had made element 114 by shooting neutron-rich calcium into plutonium. The claim was still unconfirmed, so Berkeley decided to act quickly. They wanted to keep up. So at first, Berkeley considered repeating the Russian method, but they didn't have the permission to use radioactive targets, and they had some troubles on the way. So instead, they decided to turn to the ideas of a theoretical physicist called Robert Smolenchuk, who predicted that element 118 could be created easily by bombarding lead 208 with krypton 86. It was an idea that was really unconventional, and most models suggested that this reaction would take decades to produce a single atom, but they still decided to go for it. So their attempts to create this element using fusion of krypton and lead were immediately successful. They were very surprised, and during 11 days of beam time, they observed that 3 characteristic alpha decay chains correlated in time and position to each other. And the analysis of the chains is consistent with the production of element 118 and with the theoretical prediction of Robert Swan-Jock that had triggered the experiment. The krypton and lead fused together to form element 118 before radioactively decaying to elements 116 and 114. 3 of them hasn't found yet. Well, evidently, the first member of the island of super heavy elements was synthesized. Berkeley's gamble seemed to have paid off. So because of his previous work in Germany, Ninov played a pivotal role in the experiments. He was the only one to deal with the original data, which came from the detectors in binary form and were stored on magnetic tape. He ran a computer analysis program called Goosey that converted the binary files into text files. So in 1999, no one else knew how to use the program, how to read it, how to use the numbers. So they relied on him to support the results. This is the flowchart Ninov drew in his time to his colleagues to explain the results he saw after the first experiment. So when Ninov showed the team his analysis of the data, everyone reacted with shock. The group wasn't sure it had a real detection, so they examined the results several times. They played it cautiously at first. They chose to run the experiment again after they improved the separator. They used a lot of beam schedules for a different study, but they wanted to see that they can get the same results again. Ninov's analysis revealed another event that was not spectacular, but was enough to convince that they had a real reproducible discovery. Everyone was working from numbers Ninov had obtained from his analysis. No one felt the need to examine the original raw data. So on May 99, the team announced the discovery in physical review letters. Anyone involved in the experiments was included in this article as a co-author, even the graduate students. Gregorich, the team leader, he stated in his excitement that they have actual evidence for the existence of the island of stability. I state that during 11 days of experiment, 3 alpha decay chains were observed, indicating production of 3 atoms of 118, blah, 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 in the lifetimes, and they provide strong support for the existence of predicted island of stability. It was very exceptional during those times. So when news of Berkeley's discovery were published, Hoffman's groups in GSI, the former group of Ninov in Germany, they decided to copy the Berkeley team's set to confirm the existence of this element. And this is when the trouble started. After they didn't detect any elements of 118, neither did the groups in France or Japan. Gregorich and Ninov thought it might be due to the different setups in the labs. So they agreed that the best approach would be to repeat the experiments at Berkeley. And they did so in 2000, but nothing appeared during this experiment. Meanwhile, fellow scientists were becoming confused. Ninov was behaving strange at conferences. They found him unusually evasive anytime he was asked about this new element. But Berkeley's officials were growing very nervous. Perhaps a computer program had played tricks on the research team, or some other problem has escaped the attention. So a person called Yang Li, the head of low energy research on the cyclotron, set up a committee of 3 staff members to investigate. And they made several recommendations to improve on the original experiment. One suggestion was to have several people independently analyze the raw data. Okay, So in April 2001, Gregorich and Ninov again got some beam time to retry the experiment. At first, it seemed a success. Ninov reported that the detector had picked up a decay chain of 118. But the hopes soon evaporated, and another team member, a professor of chemistry at Oregon, analyzed the raw data himself and found no evidence of the event, despite what Ninov said. Several other people, including Ninov himself, also tried again and struck out. In the meantime, some of the researchers finally looked back at the 99 experiment. They were shocked to find that there were no evidence in the original data file to any of these events. It seemed that there had been, there was nothing there. No one could make sense of the situation. The three events were in the process text file that several researchers had examined, but not in the original binary file. Most of the scientists figured that it was maybe a bug in the processing program that somehow escaped Ninov's attention and created the illusion of an event. But gradually the evidence began to fall into place. One of the team's grad students used Ninov's GUSI code to analyze the data and came to the conclusion that the events were there, but not correlated with each other. The original tape logging the raw data had been lost, but copies were stored on the computer system. The tens of thousands of pages of log data that was produced by GUSI had usually between 63 and 68 lines per page. But the page recording the discovery had 76 lines, what suggesting the new readings have been pasted into the text file using a text editor. So when the supposed discovery was examined further, it was clear that it had been fabricated. The 2001 decay chain was completely fake. But then they asked, okay, so what about the chains from 99? Analysis of the older experiment proved harder, as Ninov had worked alone and recorded his results by hand. The records horrified the investigation committee, who branded them, I quote, so meager that they fall outside the normally accepted standards for scientific research. In fact, the only record available for their discovery is contained on 2 handwritten pieces of paper. So after that, Gregorich went back and checked the original tape from 99. And it was the first time anyone ever, other than Ninov, had analyzed the data. Gregorich's conclusion was that the chains Ninov had reported with such delight, they were absent. Berkeley's element 110 was never there, was never existent. So Gregorich and his colleague issued a press release and told researchers at other labs to disregard the claim for 118. And at the same time, the team submitted a letter to physical review letters in July 2001 to retract the original findings. So in one short paragraph that offered a few details, the letter stated simply that the experiment had not detected the element 118. To the rest of the world, this whole affair looked like a simple mistake. But Ninov still stood by his research. There were much more going on behind the scenes. Ninov stood by the original data, by the original findings, and he refused to sign the retraction letter. And meanwhile, the lab appointed a second internal committee made up from computer experts this time to look into the discrepancies. The investigators had managed to obtain the original 99 GUSI files from when the computer had saved records automatically anytime a session crashed. So they say that these files show that events have been modified and added in order to make a complete element 118 decay chain before being reported out by Victor Ninov. That group determined that there was nothing wrong with the analysis program. The only plausible theory was that someone had inserted false data into the text file. And Ninov was the only person to have worked with the original data. Ninov still maintained his innocence throughout, and he said that I stand by the integrity of my research and my interpretations of the data in May 99. So while he accepted the data, that the data has been modified, he argued that his computer directories were open and his password was widely shared around the team. And it would have been possible for any of them to intentionally or not intentionally manipulate data. He says that I have never intentionally altered, invented, fabricated, corrupted, deleted, or concealed data or experimental observations, or otherwise taken any action that would result in falsifying experimental data or findings of any kind. The lab placed Ninov on a leave with pay, while a committee led by an emeritus professor investigated the matter. And in 2002, Ninov was found guilty of scientific misconduct, and the lab fired him. Only at the end of the year, the laboratory's director told all the employees about the scientific fraud that the review committee determined that took place there. And he declined to name the preparator because Ninov had filed a complaint against the lab for unfair dismissal. He criticized the Gregorich team for failing to make the most elementary checks on the preliminary data. Meanwhile, more pieces of the puzzle were emerging at GSI in Germany. Hoffman, the former employer of Ninov, and his colleagues went back to their original data tapes from '96 because they were worried that Ninov could have pulled the same trick with elements 110 and 100 up to 112. They looked through all the data Ninov was involved with by going back to the original tapes. It took several hours to see that the first decay chain of element 112 did not exist at all. It appeared only in the text file that Ninov had produced from the primary data. The German scientists then examined every decay chain recorded by Ninov from 94 to 96, and they found one more false event, that the second sighting of element 110 were never there as well. Out of the 34 reported decay chains GSI had created, 2 of them had been manipulated by Ninov. They say that, I quote, the original tape was not manipulated, but subsequent prints out were. We found them with the help of the computer center. They make backups so we could find the different versions on Ninov's computer. He added step-by-step additional numbers to make it look like a decay chain from 112. A second chain from 110 was manipulated too. It didn't exist. The recriminations of the Ninov scandal, which occurred at virtually the same time as John's scandal, John misconduct in the US, involving claims about organic semiconductors, were swift and far-reaching. The American Physical Society expanded its ethical guidelines and dedicated its conference keynote, usually given by a Nobel Prize winner, to scientific misconduct. That's it, thank you.
Great, thank you. So, as you can see, many parallels to the Sean scandal. And even he went one step further. Sean said, well, I did everything right, I trust my data. But this guy said, it's other people who manipulated the data. Okay. So he went one step further. And indeed, we went over this AIP guidelines. It was part of the lecture. It's just unbelievable to me that people go to that extent in must be something in the personality. I would think it's some kind of a mental disease that's willing to go that far. Just be aware. It's very, very dangerous, and it's outrageous. I was up on the hill during that time, and it was shoo-shoo. I did not know about this. What I did know and was that element 106. Anybody knows the name of that element? This is the only element in the periodic table that is named after a person.
Oganessian.
It's Seaborgium. And Seaborg, I knew and saw him often on the hill. He was already very old, very, very tall guy, walking from campus up on the hill every morning. But you know, his work was superb. He got a Nobel Prize for this. But all these very heavy elements were taken out of the table. They were never there. Pretty good story. All right, thank you very much. Now we are moving to the third talk today. This is Arumugam. You can share your screen.
Can you see my screen?
Yeah, we can see.
Yeah, okay. Okay, so good evening, everyone. My name is Saravan, being a student from Department of Chemistry. Today, I'm going to talk about a scientific misconduct by Dr. Daniel Antoni. So before going to the topic, let's get to know about who is Dr. Daniel Antoni. Actually, he was a young liver specialist in Liverpool University. He made huge mass spectroscopic findings for diagnosis of most hepatic inflammation. He published more than 199 research papers with the citations of nearly 10,000. In 2017, it was found that he did some malpractice and data manipulation, which is directly influenced his finding research. So he didn't respond any comments and queries from the journal editor. After that, he left the university in 2017 due to his own decision and his research misconduct. So after that, he got a position at the University of Edinburgh. However, the faculty page is now blank and invisible. So this original paper has been cited in 280 times according to the Web of Science. His main study is to study about the redox modification of HMGB1. It's a high molecular group box 1. It's a protein. It's mainly involved in the inflammatory mediators. So he mainly focused to understand the relationships when yes.
Can you speak maybe a little bit slower? It's way too fast. It's very hard to understand. So just take your time, relax, and speak a little bit slower. Go ahead.
So thank you. So he focused only to understand the relationship between the redox modification of the enzyme HMGB1. So this enzyme only expressed during the inflammation of the liver and the hepatic necrosis. So he wants to understand what happening during the redox modification of cysteine, residues of this protein, and what it will produce the cytokine protection. So he wants to oxidize or reduce the thiol group of the cysteine in the protein molecules, and he wants to confirm with the mass spectroscopy analysis. So he did all the things in the mass spectroscopy, and he published this paper in 2017, the Journal of Molecular Medicine. So after deepest investigation, the journal find that he did so much data manipulation and alteration in the mass spectroscopic graph. So
what triggered the investigation? Why the journal suspected that something is wrong?
Actually, they look at the mass spectroscopic graph. They found some mistakes in the graph. I will show you in the graph. So in this graph, they did some modifications like number changing and the superimposing and data manipulation. So we can see the changes by zooming the slides. Just a minute. Here we can see that the y-axis is not mismatching with the x-axis, and we can see the red color round. They extended the line with some halo bars, and they added some excess halo bars in the graph. And also see the x-axis labels are very, very irregular because the ticks is not similar to the others, because you can see the ticks nearly to the third decimal points. So they found some mistakes in the graph. Then they did some deepest investigation on this graph. Here also they did some manipulations. So you can see this excess bars in the graph near to the 100, and they put some excess bars. So mainly this problem is they did some manipulations in the mass spectroscopy graph. In 2020, a panel appointed from the university to take the deepest investigation about the research project, which is related to the liver inflammation.
Can you please go back to the presentation mode?
Yes. Yes. Now, okay.
Yeah.
Yeah. So in 2017, a panel from the university, they took some deepest investigation about the research project, which is related to the liver inflammation. In 2018, they produced the final report about the Dr. Daniel misconduct and his manipulation data in liver inflammations. The investigation only focused on research relating to the liver damage, because they want to know only the investigation about the Dr. Daniel Antoni. So the majority of the mistakes are only involved in the falsification of mass spectroscopy. Also, they found some mistakes in the Western blotting data and the nuclear magnetic resonance data. So he did some number changing and adding holo bars and adding lines in the mass spectroscopy graph. Till now, 4 papers have been retracted completely. So further 12 papers have been identified. Either it has having some data manipulation in the graph. So also the university also identified 14 more papers, which is containing the mass spectroscopy data, which is done by Dr. Daniel. So they found the major conclusion is data manipulation and figure fabrication in mass spectrometry data only. So they found that there is no any records for mass spectrometry analysis from the Liverpool University. They also checked in there is any proof in the outside of the university, and they didn't found any proof, and there is no any financial support for the analysis outside of the university. So what they did, as mentioned earlier, Dr. Antoni left the employment of the university by own decision in 2017. Also, the university confirmed that Dr. Antoni was entirely only responsible for his misconduct. So also the university has taken a lot of investigation about the Dr. Antoni's misconducts. Finally, the journals also alerts the people who are reading these papers about the retracted papers. So these are the publications which is contributed by the Dr. Daniel Antoni. So there are 7 papers has been retracted and is still in communication for the correction and further process. Yeah, that's it.
Okay, great. Thank you. So I just noticed that in many of these papers, there are many co-authors, there are students. So who is really getting hurt from this business? This is a PI who is manipulating the data, and the students basically don't get any credit, and you know, their PhD might be gone because of their PI. Thank you very much for bringing these questions, comments.
If the students are on the paper, please that they were part of the experiment. They took measurements. No?
Yeah, but you as a student, do you check that? Let's say the PI says, I'm going to analyze the data. I'm going to prepare the graphs. You generated the data, you give it to your PI, and the PI tells you, I'm going to do the analysis. What do you do as a student? How do you check that your PI is doing the analysis correctly?
Explain it.
Okay, but apparently this PI decided he's going to do the analysis and the students had to follow.
So he used the data from the students.
I'm just guessing, I don't know the details, but I think just because of the hierarchy and the way things work between mentor and mentee, it will be extremely difficult for a mentee to criticize his mentor. It's your scientific future. You want recommendation letters.
Actually, students are supposed to do data analysis.
Of course, a good PI will ask the students to do the analysis first, and the PI will check the students' analysis, not the other way around. I'm just guessing. I don't know that it's happening.
This is similar to the case we did about the psychiatry,
Right.
doctor which fabricated experiments.
Yeah, so there is always an issue. It doesn't matter who is doing the fraudulent job, the student or the mentor. This relationship is a difficult relationship. You know, at the beginning of your PhD, you know nothing. Your PI is God. By the end of your PhD, you know on your topic more than your PI, and you are the expert. And so the relationship is changing over time. It's all about trust,
Yes.
and correct conduct. And once this breaks, you know, you can get to this type of situation. But the people who suffer from this case are the students. Very sad. So be kind to your students when you grow up and become real professors, right?
If the professor gets his PhD status, cancelled, about the PhD students, what should
I don't know. It's a problem for the university. Depends when they are on their trajectory towards finishing, right?
about the psychology?
Let's say this guy they find that the misconduct, they can transfer the students to another mentor, right? Another PI, and then the new PI will say, okay, just do this little tiny thing. Let's write a paper together and you graduate. So, you know, there will be some accommodation usually. But if the student's already at the end, that's a very difficult situation.
Or if they're done already.
Done already and moved on, yeah.
Also,
Yeah. No simple solution. Great, thank you. You can unshare your screen. And the last talk of the day is by Sri. Sri is here, great. So yeah, you can just share.
Can you please let me in the...
Did you log in?
Yeah.
So what is the issue? The meeting host will,
Let you in. So
I don't see.
into the view.
Oh. Okay.
Yeah. Okay.
Recording in progress.
Allowed me to share the screen.
I did. Which? And my speaker should be off. Okay, good.
Yeah.
Let's go to presentation mode. Yeah, great.
So
Okay, go ahead.
I have muted myself in the Zoom as well as in my system.
You're good. Just
Okay,
go.
fine, yeah.
Speak up.
Yeah. Today I'll be talking about the invention of lithium-ion batteries, and further I will be talking about some of the retrospections of Nobel community, where only very few people or many people who are not acknowledged by the Nobel Prize Committee. So first, coming to the invention of lithium-ion batteries. So let's see how the lithium-ion battery works in the beginning. So in all the mobiles that we are having, yeah.
Oh, that's me. Sorry. Go ahead.
Yeah. So lithium-ion battery has mainly three components. One is anode. This is anode, and the other is cathode. And there is some space between these two, which is called electrolyte. And we have a insulation sheet between these two components. So as you see, here you see the car is charging now. So during charging, the lithium ions are coming from cathode to anode. This is graphite or carbon sheet. So during discharge, like when we are using a mobile right now, so all the lithiums are coming from anode to cathode. So this is how the shuttling of lithium ion happens from one side to other side when we keep charging and discharging. So the first lithium ion intercalation phenomena was explained using titanium sulfide cathode materials. So this is the first paper that Stanley Whittingham has published in Science in the year 1976. So this is the only figure in the paper. So this figure majorly depicts that the curve in the figure 1A. 1A shows the open circuit voltage of the cell at different percentages of lithium in titanium sulfide, and the curve B shows the discharge curve, meaning when the lithium is getting back inside that metal sulfide. So how is the percentage of lithium coming back? So how much amount of lithiums, like if it is 10 milliamps, it can be like converted into the lithium atoms corresponding to the number of electrons that we are drawing. So this is the B. The curve B is like discharge curve at 10 amps till 0.3 or 4 milliamps discharge till it gets completely intercalated to lithium ion. And curve C is after discharge of 1100 cycles of charge discharge cycles. As you see here, the voltage window of this specific cell is between like around 0.1 or 0.2 to 2.5 volts. So in the first paper itself in the year 1976, so he had showed 1100 cycles of charge discharge cycling of this specific battery. And the figure 2 shows discharge characteristics in lithium aluminum chloride and methyl chloroformate. So methyl chloroformate is the electrolyte in which lithium aluminum chloride is the salt which migrates from anode to cathode. So it's like we have a reservoir in the battery, but we needed something for this migration of lithium from one side to other side. So this is what the lithium salt and the electrolyte does. So further in 1980, after like 4 years, as you see in the voltage y-axis is the voltage. I'm sorry, I haven't presented the voltage title here. So it is the voltage, like it is extended to 4.2 volts from 2.5 volts, which in case of metal sulfide, titanium sulfide. So this has happened because of the cathode material, which is lithium cobalt oxide. This was first reported synthesized material by John Goodenough using lithium carbonate and cobalt acetate using solid state method. So when this metal oxide has been the cathode side of the lithium-ion battery, so we are able to gain more number of lithium atoms per gram of cathode. So in the other words, we are able to shuttle more number of lithium ions from anode to cathode. Thereby, we got more number of more time of charging and discharging. So this is the series of significant inventions happened in the lithium-ion battery. So first paper was in 1976, so by Stanley Whittingham, and further lithium cobalt oxide by John Goodenough. So further, it is Akira Yoshino from Japanese chemist, who had patented that. So instead of using lithium metal as a reference on the anode side, he had used a cost-effective carbon anode from petroleum coke. So he had patented this as a US patent. So so further it was commercialized in Sony, which has revolutionized the lithium-ion storage, like portable energy storage systems. So further, there is continuous progress to improve the lithium-ion capacity in the cathode material. So the graph that you're seeing is the storage capacity. The x-axis is the capacity. It's nothing but number of lithium ions that you can store per gram of the material. And this is the voltage window. So further, what happened was, so as you see here, the green curve, lithium cobalt oxide, some percentage of the cobalt is replaced or substituted with nickel or manganese. So when they have replaced some percentage of nickel and manganese, they have seen higher voltage stability of these materials. And not only that, they have observed increasing in the lithium-ion storage capability in these materials. It is because of the redoxability of the cathode, like nickel and manganese. So even the rest, all the other materials are also like more competent to like NMC, which is popularly commercialized now. NMC is like one of the attractive because of its thermal stability and low cost, as we are decreasing the percentage of the cobalt. So the cost of the overall cathode has decreased. So this NMC, which is nickel manganese cobalt oxide containing lithium, is a rhombohedral symmetry with R3 space group. And especially when we increase the percentage of nickel, it has higher redoxability and higher storage of lithium ions in the overall cathode material. So when we remove the lithium from this cathode material, all these transition metals like nickel, cobalt, manganese, they go to higher oxidation state in order to compensate the ionic charge balance. However, there are several parasitic reactions or structural degradative losses that occurs when we keep charging and discharging. This is the reason why after like 1 or 2 years, the efficiency or the time that we need to charge our battery goes down. So these were the major parasitic reactions, degradative reactions in metal oxide cathode materials. So especially here, as you see here, the structure, the red color atoms indices that you see here are the oxygen atoms. So there is a release of oxygen atoms when we try to extract approximately 80% of lithiums from the cathode material. So which will lead to electrolyte degradation because oxygen is highly active. And electrolyte are majorly this organic species. So as a result, with the reaction of oxygen, they form organolithium species. And not only that, there is surface reconstruction from layer to spinel and further to rock salt because of the loss of oxygen here. And lithium plus and nickel plus 3 exist of almost similar radius. So because of which lithium gets diffused to nickel, or nickel gets diffused in the channels of lithium. And there is manganese dissolution. And when we charge and discharge for longer period of time, there is overall structural loss of the material. So which is seen as intergranular cracking, which will lead to higher electric resistance in the cathode material. So how can we mitigate these parasitic reactions? Many of the ideas proposed to mitigate these parasitic reactions are surface coating or doping. So surface coating, by using surface coating technique, we are creating an artificial electrode-electrolyte interface, so which will suppress these parasitic reactions, and thereby it will improve or retain the electrochemical stability on longer cycling. So in this regard, further, Stanley Whittingham has reported surface coating of NMC using lithium niobium oxide for improving the electrochemical properties. So how did he do this? So he had continued to improve the efficiency or the capacity of the lithium, and further coping up these parasitic reactions on the cathode material. So this is the wet chemical method upon which he had developed a lithium niobium oxide coating on NMC. So basically he had taken niobium ethoxide and NMC oxide, like nickel, manganese, cobalt oxide material, and he had done ethanol evaporation in a simple beaker. So this had led of surface coating and substitution of niobium into the NMC. So this is confirmed by high angle annular dark field scattering transition electron microscopy and EDS for elemental mapping. So which had shown the surface coating as well as substitution of niobium in the NMC. So in the figure H especially, you can see the surface coating and as well as substitution inside the NMC particles. So rest all the E, D, E, and F are the elemental mapping of nickel, manganese, and cobalt. So the figure A and B are the cross-sectional images of the NMC particle, in which you are able to see the coating as well as a small percentage of substitution of niobium inside the NMC. So when they have conducted the electrochemistry of this, so they have seen improved electrochemical properties for 3% of lithium niobium oxide coated NMC 811. As you see, the black color rectangles here are the pristine, which is not coated. It has retaining 200 milliampere hour per gram capacity in the beginning, and later after 60 cycles, it has dropped to 40 with the loss of 40 milliampere per gram. So at 180 milliampere per gram. So whereas in case of 3% lithium niobium oxide coating, it has decently stabilized the NMC 811. So this shows that this surface coating of this lithium niobium oxide on NMC has protected the NMC 811 upon prolonged cycling, and also against parasitic reactions that we have discussed before, like oxygen loss or electrolyte degradation, etc. So Sony has got the first credit for commercializing this lithium-ion battery with low-cost carbon anode. And as we see that since 1990s, the portable energy storage has been changed with this invention of lithium-ion battery technology, and there is constant research going on to improve the lithium-ion battery for deployment of electric vehicles. So so far so good. Like if we have seen so many people getting recognized with Nobel Prize so far, but is there any people who are not getting recognition or not who are ignored in spite of working so hard? So when I'm looking on this aspect of idea or in this on this retrospection, so I found a beautiful article saying that it's a most recognized and important. However, there are controversies and distorts the public perception of the science, and because it excludes many of the scientists who had contributed to discoveries. So this is a beautiful paper from Weizmann Institute of Science. So the first Nobel Prize was awarded in the year 1901 to Emil von Behring for the discovery of antitoxin for diphtheria. So this discovery was made 10 years earlier with a collaboration of a Japanese physician and bacteriologist with Baron Kitasato. Even Kitasato was one of the nominees of the Nobel Prize, but he was not given the Nobel Prize, stating that it is only for one person the Nobel Prize will be awarded. However, on the next year, two people had shared the Nobel Peace Prize, and a year later, like two Dutch Nobel laureates, Peter and Hendrik, were chosen in the field of physics. As we move on, in 1952, Nobel Prize in Physiology and Medicine was awarded to Selman Abraham for the discovery of antibiotic streptomycin. But it was actually his graduate student, Albert, who had discovered the antibiotic while he's working alone in the basement laboratory. Further in 2003, the Nobel Prize Nobel Prize was awarded to Paul and Peter for developing magnetic resonance imaging. But it is Damadian who had first presented the idea of MRI and who had first published the article in Science on tumor identification using MRI. But he was never acknowledged by the Nobel Committee, in spite of first invention and publication of his MRI work. And further, in 2017, Nobel Prize was awarded to Rainier, Barry Barish, and Kip Thorne for LIGO observatory team. So they have received a Nobel Prize for their contribution on discovery of gravitational waves. However, the three who had founded the executive committee of LIGO form part of team of hundreds of researchers. The article describes the discovery of gravitational waves, which is authored by more than 1,000 people from 20 different countries. So there is a limitation that the Nobel Committee is not awarding more than 3 people later on, nor the group in group. And what about the Nobel Prize for Women? Out of 262 researchers who received Nobel Prize in Sciences over the existence of this Nobel Prize, only 22 people were women, in which Ada Jonathan, who shared 2009 Nobel Prize in Chemistry for resolving structure of ribosome. And another female researcher who specialized in resolving molecular structures was British scientist Rosalind Franklin, who made significant contribution to the resolution of structure of DNA. As Simon was saying, her colleague Maris Wilkins shared an image she had produced with Watson and Crick without her knowing, which allowed them to determine the structure of DNA in further, and they have published it without her notice. So Watson and Crick and Wilkinson were awarded the Nobel Prize, ignoring Franklin, and after 4 years, she had died with ovarian cancer at the age of 37. And further, living female scientists were also marginalized by the male colleagues and opponents. Vera Rubin, an astronomer during 1960s and 70s, had discovered the evidence of existence of dark matter based on the deviation of movements of galaxies, has been mentioned many times as a nominee of Nobel Prize in Physics. However, even after awarding 2011 Nobel Prize in Physics to 3 men who discovered dark energy during observations, which were carried out 20 years after Rubin's observations. But the Nobel community continued to ignore Rubin's achievements without acknowledging her. And further, Australian-Swedish physicist Lisa Meitner rightfully deserved a Nobel Prize, but in spite of being nominated for 48 times, she never received it. She had discovered the nuclear fission together with her nephew Otto Frisch and her longtime collaborator, German chemist Otto Hahn. Meitner accompanied Hahn to the award ceremony, but was disappointed by the fact that he didn't even mention her or Frisch's contribution during his Nobel Prize speech. And other scientists who have not received the Nobel Prize, who have believed that they have not received the Nobel Prize, are Nikola Tesla and Thomas Alva Edison, people who doesn't require any introduction for their contribution towards science. And Satyendranath Bose, who invented the boson particles. Boson particles are the subatomic particles responsible for the, I read it that they are responsible for the physical interaction and influences the electromagnetism or the gravitational waves. And during a conference in Kolkata, in India, in 2012, a renowned German physicist had mentioned that it is ironic that Bose was not awarded the Nobel Prize in spite of his immense contribution towards physics. And what could be the possible solution for this? In the 3 wills of Alfred Nobel in 19th century, he had mentioned that it is only in the beginning, only one person will be awarded in the 5 different fields of sectors of the sciences in which the people can be awarded. So the possible solution could be abolishing the limitation of the number of researchers who can win the Nobel Prize, such that every people who had contributed can be awarded as a group, which will be encouraging for the scientific community. And further, more inventions. So this is what I thought to present so far.
Great.
Yeah.
Thank you.
Yes, thank you.
So regarding the first part of your presentation, are you suggesting that lithium-ion battery should get the next Nobel Prize?
Yeah.
Maybe.
For me.
Well, it's very useful technology. I think you went way too much technical detail. That wasn't the intention. The whole topic of the course is really about scientific conduct. And therefore, I found your second part more interesting. And almost every year of every science Nobel Prize given, you will find some criticism about people who also deserve it, because science is evolution. It's hardly revolution, although we tend to think that, yes, a Nobel laureate really made something huge. And in fact, the way Alfred Nobel formulated the rules, that need to be really a jump, not a small step. That changed things dramatically. But in all cases, you will find that some people did some work, part of the work earlier. I remember when Ahmed Zweil got his Nobel Prize for femtosecond pulse chemistry, I was sitting in Bell Labs with Eric Eppen in the same room. Eppen and Chuck Schenck invented the femtosecond laser, and they didn't get it. And it was so obviously a mistake of the committee. Almost every year you will find some people who did some important contribution for that prize. So you gave a few examples, but it's very hard job for the committee to make that decision of up to 3 people, when in every field there is evolution of ideas, and oftentimes many people think about the same idea more or less independently in 2 different phases, just because of the background of accumulation of new knowledge. So I think it's a good topic, and Nobel Prize is not perfect, and there are mistakes. And a very, very good example is Ashkin, Art Ashkin. In 1997, Stephen Chu got his Nobel Prize for cooling atoms. The idea was Ashkin. Ashkin was Stephen Chu postdoc mentor in Bell Labs, and they started to work with polystyrene beads. And then Steve Chu got his member of technical staff position, went to the other lab in the end of the corridor, didn't talk to Art Ashkin, who was his mentor, and pushed for this atomic cooling idea. I was in 2 Nobel conferences in Sweden One was immediately after Steve Chu got his Nobel Prize, and Art Ashkin was invited. And he was very, very bitter, extremely bitter. Just 2 or 3 years ago, Art Ashkin got his Nobel Prize when he was 97 years old. And a few months after he got it, he died. You know, you can get the Nobel Prize only when you are alive. So there was a correction. This is the only correction I know of. Somebody should have gotten it, didn't get it. And some years later, somehow, the committee decided that they really made a mistake and they should correct this. So that's the one example where there is a correction. Even
John Goodenough was received Nobel was 97 years old.
Yeah. But that's in chemistry. Steve Chu got it. Okay. In physics. All right, guys, this brings our course to conclusion. It was a pleasure, you know, interacting with you and sharing some of my ideas on this complicated topic. And I wish all of you great good luck here in person in the room and in Zoom in your scientific careers. And hope to see you sometime as you develop your careers. Good luck to everybody.
Thank you all for your attention.
And bye-bye, everybody. Good luck.
Thank you.
Bye.
Bye-bye.